Hello dear students, let's come back to type 0 grammar and understand more about this type of grammar. Now as you all know, type 0 grammar is called regular grammar and it is nothing but expressed as regular expression. And the rule about regular grammar is that all the right hand sides have a restriction. Right hand side can contain a single terminal followed by a single non-terminal, or right hand side can contain only one terminal. Okay, now what I want to prove is that this regular grammar indeed is nothing but a regular expression, and it can be implemented using DFA or NFA. Just see how we can construct an FSM. This is also called as finite state machine. Very easily, following some really simple steps, you can convert this regular grammar, or you can implement this regular grammar or regular expression, whatever you call them, as FSM, finite state machine. Now just make out what are the non-terminals in this given grammar. S and A, correct? Two capital letters. And then terminals are A, B, C. And the productions P are, I'll write them just to make clear, is the first production is A derives AS, correct? Second production is S derives BA. I have just split this OR operator to make it very clear. Okay, and then the third production is A derives BA, and the fourth production is A derives C. These are the productions, and the start symbol obviously is S, which is the top left symbol written in our regular grammar. This is the regular grammar. Okay, what I was telling is you can take these productions one by one and you can easily translate this into a DFA. What you do first is all the non-terminals, will be represented as the states of DFA. You recall DFA has states Q0, Q1, Q2 and so on. So now the non-terminals are S and there is one more non-terminal A. So you represent them as the states of the DFA, and who is the start symbol, by the way? S is the start symbol, correct? In your grammar, S is the start symbol. So you represent this S as the initial state. The start symbol of the regular grammar becomes the start state of the DFA. And now you typically add one more state called final state. It's not there in the given grammar, but then you add this final state, and as you know, final state of DFA is double circled or double oval. Now you define the transitions. Let's take the first transition. S derives AS. Now you define this as whenever S reads A, small a, of course, the terminal, then the machine remains in S. Look at this. S reading small a, machine will remain in the state S. So this becomes first transition. Now you just check second transition as I am underlining here. Whenever S reads small a, the machine enters a new state A. So whenever capital S, this state, start state, reads small a, okay, the machine will enter, oh, I'm so sorry, this was B, I'm so sorry. Yeah, this was BA. Just check, this is BA. So whenever a machine reads B in the start state, machine will enter the state A. Now have a look at this. How do you define transition for this? Whenever machine reads small b in the state A, machine will stay in state A. So there will be a loop here. And now how do you read this? A determines C, the last one. Whenever machine reads small c in the state capital A, machine will enter final state. See, the small c in capital A state, in this A state, will take us to the final state. You can see that there was no state here. There was no state. Like every transition had a state defined, but there is no state here. So we replace this with capital F. Now trust me, this is so simple. This is so simple. Now you can see that this is indeed the DFA, which will generate the regular language. generate the regular language. But what is the regular language? It is same as regular expression. What is that? You can see that in the start state you can get 0 or more A's. So that's A star followed by B. Compulsory B, one B must be there, and then 0 or more B's. Look at this loop, 0 or more B's, and then followed by C. That's it. How will you describe the language? This language has all strings which has 0 or more A's, followed by a compulsory B, single B, followed by 0 or more B's, and all the strings end with C. Compulsory, the last letter is C, and there is only one C, one single C, one C at the end of all the strings. If you are getting confused, let me tell you, regular grammar, regular expression, DFA, NFA, FSM, all are same. All do the same work of accepting regular language. Please try to understand this. This is the machine, the automata, which is going to actually realize or actually implement this regular grammar. Let's check one more example about regular grammar. A very quick review of this. Suppose we have some arbitrary grammar like this. S derives A, S, okay. Then S derives, let's say S derives B, A. Then A derives, let's say A derives C, B or D. Then B derives, let's say D, B or E. Now all the right hand sides you observe are following the regular grammar rule, correct? Now how do you construct a DFA for this? First of all, which are the non-terminals? S is a non-terminal, A is a non-terminal, and B is a non-terminal. So all of them become the states, and one more state, capital F, which is the final state, will be added. And the start symbol is S as visible over here. So S will be the initial state of DFA. How do you define this transition? When S reads small a, it remains in same state S. When S reads small b, it goes to a new state A. When A reads small c, it goes to B. When A reads small c, machine goes to B. And when A reads small d, there is no state here, you watch. Replace it with F. That means when A reads small d, it goes to final state. How do you define this transition? B derives small d followed by capital B. B derives dB. B derives dB means you will get a loop here. And B derives E means there is final state over here. When B reads small e, you will go to the final state. Just observe that this is the DFA which actually implements this regular grammar. But I said regular grammar is same as regular expression. You can express this whole thing, entire thing, as a regular expression. Correct? But what is the regular expression? You can see that at the start you can have 0 or more A's. That means A star. Then there is a compulsory B. There has to be a B which will take you to A, and A will take you to the final state. So there has to be compulsory B. And then you can see that you can either have C, or D. You can check here. There is OR over here, isn't it? From A, you can either go directly to F or you can go to B. That means there will be something like C plus D. I hope you are understanding. C plus D. So after AB, after some number of A's and compulsory B, you will get either C or D. That is C or D. That's what I have written. Correct? But what if you get C? If you get C, then you can have many number, 0 or more D's followed by E. Correct? So it's better to group one particular part like this. You watch. First we wrote something and then just erased it because we got an idea that after this B you can have C, okay, C, then you can have D star. After this C you can have 0 or more D's followed by a compulsory E which will take you to the final state, or just check the or here, or you can get D. Just D will take you to the final state. So after 0 or more A's followed by B, you can either have this section or directly D, which will take you to final state. This regular expression, this DFA, this regular grammar is all same. It's only a way of representing them is different. So that's why we say regular grammars generate regular language, and any regular language has a DFA, and any regular language can be expressed as a regular expression. I hope the things have become more and more clear about type 0 grammar. By the way, we are learning type 1 grammar in this chapter, that is CFG, and more about CFG and push down automatas is coming up. Well, type 2 and type 3 grammar, be patient about that. Type 2 and type 3 grammar, that is unrestricted grammar, will be seen as we approach our subject, but not now. I am just delaying the discussion of type 2 and type 3 grammars. Okay, so see you in the next video with more about CFG, context free grammar. Thank you very much.